Welcome back everyone to another exciting video in the PID control tutorial series presented to you by FRC Team 2168, the aluminum Falcons. During this lesson I'm going to show you an easy to use method to determine the gains of a PID controller using Matlab and Simulink that requires no previous control theory knowledge. We're then going to implement those gains in our LabVIEW project, run it on our C-Rio, and observe the response of our system. I'll then show you how to modify the gains to improve your response based on what you observe. And then finally, at the end of the video, I'll have some discussion on some pitfalls and other things to watch out for when tuning a PID controller. Just a quick note, this video is one part of a series on this topic, so if you haven't done so already, please go ahead and check out the preceding videos before you continue. A lot of what we cover in this video is based on what we've previously accomplished. So let's get started. The first thing we're going to do is open up LabVIEW and open a project that we previously created. If you haven't done the walkthrough with us, all the files that we use in this tutorial are available for download from our team website. Mine is saved on my desktop, so I'm going to go to File, Open, Project, navigate to my desktop, and open the project file. So before we start tuning our gains, the first thing we want to make sure is that our hardware is set up and that we have proper command and control. So what we're going to do is deploy this code as is on the C-Rio and use the GUIs that we created to make sure we can manually command the motor and properly read the values from the encoder. Now before I started, I already made sure that my connections were correct and that my A and B channels from the encoder were plugged into the proper digital input pins on the digital sidecar that I specified in the begin VI. I also checked my PWM cable going to the motor controller was plugged into the proper PWM slot that I specified. And then lastly, I verified that my battery was fully charged. You want to make sure that you have a fully charged battery or the response of your system is going to underperform. So what we're going to do is open up Robot Main and just run this code in real time on the C-Rio. We also need the driver station open. And while that's loading, I'm going to hit run in Robot Main. We can minimize the dashboard. And even though I'm using the new version of LabVIEW 2011, I'm still using the old driver station, so I need to disable the stop button. So I'll go ahead and do that. Okay. Now there are three main VIs that we're interested in looking at to confirm our robot's restarting because I have my computer plugged directly into the C-Rio. So the three VIs that we want to look at, teleop, periodic tasks, and simple PID. I'll briefly describe what we're looking at here. The teleop VI. L2 motor represents a slider. It's basically a joystick controller that we can use to manually control the motor in the forward and reverse direction only when this switch is switched over to manual. When it's switched to PID as shown, we no longer have manual control of the motor, but instead the motor is controlled automatically via the PID controller, which is governed by these P, I, and D gains. SP is short for set point, and this slider represents our desired position that we'd like to drive the motor to. Wheel serves two functions. One of its ticks represents the current position of the wheel based on the encoder output, so it will track the encoder output that we get from periodic task. Another tick that's on this wheel tracks our current set point. So this wheel will show both our desired position as well as the current position, and we'll use this to have a visual representation of how well our motor is tracking our desired position. These inputs here are other inputs to the PID controller that allow for more advanced functionality. Max negative output and max positive output allow us to control the maximum output of the controller in the positive and negative regions. Now this is technically used to prevent saturation of the controller and coerce the controller output to match the input values of the motor controller. However, in our case, we can use these inputs to control the max speed of our controller in the forward and reverse direction. -1 and +1 will be full speed. Setting these values lower will allow you to run your motor at a lower maximum speed if you desire. The min negative output and the min positive output allow us to control the minimum output values of the PID controller when an error is present. And this is basically used to overcome any deadband that we might have in the lower region of the motor. Acceptable SS error. This is short for acceptable steady state error. And this allows us to basically set the precision that we'd like our controller to have and what error or what offset from our set point we can tolerate. We'll see how this can be a great feature to have. Enable gain schedule. We'll talk more about this later in the end discussions on more advanced topics. So let's switch over to periodic tasks. This is just the generic VI that shows the outputs of our encoder. So we'll show the encoder distance, which is in inches, the direction, either backward or forward, and the rate, which we're not interested for this tutorial, but it would be handy if we were doing speed control. This waveform chart just basically graphs the output encoder distance with respect to time. Doesn't really serve much purpose. Simple PID. This front panel is a useful tool that I put together in order to not only help us tune the PID gain, but it will also show us what's going on in our algorithm in real time. We'll be looking at the output variable. This is the output of the PID controller, which is input to the motor controller. P used, I used, and D used are here to show us what values of the PID gains are being used. And I'll explain more about why this is here. This is only useful when we have gain scheduling enabled. Proportional, integral, and derivative show the real-time portion of the PID controller that makes up the output variable. Error sum shows the running error, and controller output unsaturated is just something that I use on this waveform chart to allow you to see how the saturation values of max negative and max positive are used to prevent saturation of our PID controller. And this waveform chart is going to be a very useful tool to see how the PID controller is reacting as we're switching our set point value. So what we're going to do is first make sure, very important, that before we enable, we're always switched over into manual mode. If not, and if this set point was set somewhere, the PID and the motor would just jump off and we wouldn't know what was happening. So we're going to enable, and we're going to slowly drive our motor forward. Okay, and we can see we're getting positive distance. Our encoder direction is forward, which is correct. And we're also reading rate correctly. We're going to try, and you can see here our slider is increasing. We'll try the reverse direction. Now our current, even though it's not shown here, our current value ticker still tracks the encoder. Since this wheel only stops at 500, this little slider, which represents the current position, won't go past it. We can easily extend this to be, 1,000 or more, depending on what we think our operational range will be. For now, I just have it between 0 and 500 inches. Let's try the reverse direction. And as you can see, the encoder is now counting down, going in the reverse direction. The slider is going down. We're moving backwards, and we're reading rate. So it looks like we're positively able to command the motor as well as read the encoder properly. So from this point on, we've confirmed that our command and control works, and we know that our hardware is working properly. So if we run into any problems from this point forward, it's more than likely going to be a software issue. So now that that's done, let's switch gears and figure out what our gains are. So let's open up Matlab. Now I'm using version 2011 for this tutorial. For this to work for you, you're going to need at least Matlab 2009, Simulink, and the control system toolbox installed in your machine. If you don't have any of those items, although it's not included with the software that comes with the kit of parts, first it's got to deal with MathWorks to provide free licenses for first teams. All you have to do is email MathWorks. I provide details on how to do this in a previous video. So if you haven't done that already, go ahead and get those free licenses for your team. The first thing I'm going to do is cancel or exit out of all these windows. And I'm going to go to desktop, desktop layout, click on default, and then maximize. This way we're both looking at the same window. I'm going to add one more. So go to desktop, editor, and you'll see this window. By clicking and dragging on the top of the window, you can reposition it. I'm going to just place it above the center. So now you'll have current folder, editor, workspace, command history, and the command window. Now if you have Matlab installed but you're not sure if you have Simulink installed or the control system toolbox, or you're not even sure what versions of the software you have installed, the version command will be helpful to you. Simply type in VER in the command window and hit enter, and Matlab will return everything MathWorks that you have installed. And as you can see, it tells you that I have Matlab version 7.12, which is 2011 installed. I have Simulink version 7.7, which is 2011 installed. And if you scroll through my toolboxes, I have the control system toolbox installed. So make sure you have at least those 3 items before you continue. So the first thing I'm going to do is click on the editor window, go to open, and navigate to the folder that you downloaded from our team website, and open the Matlab folder and open the .m file. Now when that opens, you're basically going to see a text file that opens up. And this text file is a script that will instantiate all the variables that we need that represent a mathematical model of our system. All the values that we calculated in the previous lesson are now put in here, so you can see that we have all the parameters that we specified. Our motor parameters, which are motor inertia, viscous dampening, motor torque constant, motor back EMF constant. We have the armature properties, the resistance of the motor, and the inductance of the motor. We also have our load properties, our load inertia, and any viscous dampening created by the load. And lastly, we have our gearing ratios. Transmission represents the gearing ratio that the motor is plugged into. So in this case, I have the Andy Mark Sim gearbox. So it's a 12:75:1 ratio. The secondary gearing ratio is any gearing that you might have between your gearbox and your load. And in this case, I have some sprockets on my setup which result in a 12:22 gearing ratio. Sampling time, I don't need to worry about it. Just leave it as is. Don't remove it. So what you're going to do is when you open this up for the first time, you're going to enter your properties in here for your motor. Whether you're using a sim or not, you're going to leave the variable. You're going to leave everything to the right of the equal sign constant. So you're not changing JM equal. You're just changing the values before the semicolon. Make sure you terminate your value with a semicolon. This is a programming language, so everything needs to be terminated with a semicolon. It may look a little different because I don't do something that you might be familiar with, like int or double. Matlab is a non-declarative language, so you don't need to do those things. When Matlab runs this code, what it will do, it will create a variable JM and have this value equal to it, and it will do it for each one of these things. As you can see, I already have the values that we calculated for my apparatus saved into this text file. What you're going to do is you're going to go in and type in your motor properties. You're going to type in your load properties and make sure that you calculate the proper inertia of your load. The transmissions are pretty simple, are pretty straightforward. Motor side and output side that you plug your motor into, and then the gearbox side and the load side from anything after your gearbox to the load. Simply just change those values. Alright, so what we're going to do now that we have this all set up correctly, I assume that you have yours all set up correctly too. We're going to hit this green play button, which is just run. You can do a keyboard shortcut, which is F5. And what it's asking me is MATLAB is like any other development environment, and it's asking me to change my workspace to match the folder that I'm running in. So I'm going to go ahead and click change folder. And when I do that, you'll see you get these yellow boxes in this workspace. Workspace represents the memory that you're currently using for your application. And in this case, it shows all the variables that I have currently instantiated as well as the value. So this is a handy window to have open. So that's it for this part. Let's go ahead and open up Simulink, and you do that by clicking on this funny little icon here. And another check to see if you had Simulink installed was if you did not have it installed, this would be grayed out. And if you did have it installed, like I do, it will show in color. So when you click on Simulink, when Simulink opens up the first time, you see a window like this, and what we're going to do is go to Open, navigate to the MATLAB folder again that you downloaded, and we're going to open the .model file or .mdl file. And that opened up here. So first thing you want to do is go to View, Fit System to View, so you can see everything. And what you're looking at is a block diagram of the complete feedback controller loop. And I'll just briefly walk you through what each of these boxes are doing. Starting with subsystem 1, this is something that I put together that represents a mathematical model of a motor driving a load through a gearbox. It takes an input voltage and it outputs the degrees that the load has spun or the speed that the load is spinning at. And since this is a position control tutorial, we're using the degrees output. You can ignore zero order hold or all these things for now, but basically we're reading the output of the load and we are comparing that to our input, which is represented by this step function. And the input is our set point, our desired position that we want to go to, and we're subtracting the two, and this represents the error. We provide that to the PID controller block. This block represents the PID algorithm, and it will crunch on the error that we give it and provide an output, and its output will feed the input voltage of our plant, and that's the control loop, and it will keep doing this and doing this over and over and over again until this value goes to 0, this error value. And the way this goes to 0 is when our set point and our current value match. When this is 0, then no matter what gains we have, anything's times 0 is 0. So the output will be 0 volts, and that will cause our motor to stop. Once this error increases again, because our set point has changed or the wheel has drifted, somehow they've come out of sync, then our PID gains will then act on those error values once again and drive our input voltage accordingly. Zero order hold is a function that converts a continuous time signal to a discrete time signal using a specified time sampling. And the time sampling that it is using is the sampling time that we specified over in MATLAB. So if you double click on this, you'd see T for our sampling time that we specified. If you double click on subsystem 1, what you're going to see is this function block parameters window that opens up. Let's expand this. And basically this is a mask for all of the parameters that you can set to modify this plant. And we have everything that you saw in the MATLAB text file. Motor back EMF, motor torque constant, the motor inductance, the load inertia, the transmission gear ratios, and the gear ratio between the transmission and the load. So this is a good time to talk about how MATLAB and Simulink interact with each other. Any variable that's in your workspace that you created in MATLAB is instantaneously available to Simulink. So for example, I instantiated JM, which has this value in MATLAB. In Simulink, in any part of Simulink, I can use JM instead of that value. You have two ways that you can populate these parameters. You can go ahead and type in the numeric values, or you can declare your values in MATLAB and then type in the variable name. I prefer to use the latter method, and I'll show you why. Just hit apply first. When I use when I just simply put the variables in here, I can leave this block as is and I don't have to change it. All I have to do is simply go to Matlab and I can modify these values, hit run again, and those values will update. The reason why this is beneficial is I can use this as a design tool. Let's say I'm trying to design my controller and I'm not sure if I want to use a sim motor, if I want to use a BaneBot motor or a window motor. I can create a new text file, go ahead and Control A and copy everything here, paste it into my new text file, call this, motor 2, change the parameters to represent another motor of choice, and let's make up a number right now. Let's just say it's 2e to the minus 5. I can save that as motor 2 .m, and when I run this, you'll see my JM now updated to what's in here. I can switch back. Let's say I can switch back to my original design, run this, and my JM is now taking on the value here. I can modify my plant represented by subsystem 1 I can modify my plant and save a new text file for each variation on my hard drive without ever having to modify my model, because these values all stay the same. So that will allow me to hot swap between different designs instantaneously, and then I can see which design works best for me. Maybe the BaneBot motor is better, or maybe the sim motor is better, or I can play around with different load parameters, seeing if a larger wheel or a smaller wheel will work better for me, or change my gearing ratios and save all of those configurations in a new text file without ever having to go into my model parameters and modify any of these. So you can do them either way by entering the values here, but I highly recommend you implement all of your variables in Matlab and just reference those variables in Simulink. So I'm going to leave this as is and hit OK. Now what we're going to do is we're going to jump into the PID controller. So double click on that, and what will open up is this PID controller function block. I'm going to show you what you're looking at and how to set this up. So for the controller, this represents the type of controller that this block should mimic. And you have the full gamut of options. You have a PID controller, a proportional integral controller, a proportional derivative controller, simply proportional, or just an integral controller. For this tutorial, I'm going to show you how to tune a PID controller. And if you can tune a PID controller, you can tune any one of these guys. Form, we're going to leave as parallel. The other option is ideal. The difference between the two, as you'll see, is when I select ideal, the formula that MATLAB uses to calculate the gains change. As I said before, there are many different ways to implement PID controller. In the ideal case, the proportional value affects the output of the integral and derivative value. In the parallel case, and that's the case that I implement in the simple PID VI, you can change the proportional, the integral, or the derivative gain without affecting the other two parameters, and it's easier to tune that way, and it's more intuitive to a beginning user. So we'll leave it as parallel. Time domain is continuous time. The controller parameters, these represent the current PID parameters. Just ignore whatever values these come up with initially, but they all have to be real positive numbers. If any of these are negative, you're going to get an error that it spit out at you. Initial conditions, source is internal, integrator and filter are set to 0, and external reset is none. Make sure this is unchecked and zero crossing is checked. We'll go over to PID advanced. Check the limit output and set the upper and lower saturation limits as such. Ignore saturation unchecked. The anti-windup method, we're gonna set to clamping, and I'll explain more about what this is later, but clamping is a method that I use in my simple PID algorithm to prevent integral windup. Tracking mode we'll leave unchecked. Switch over to data types. All of these should be inherent via internal rule, and these guys are all blank. These should all be set as shown. State attributes should just be empty with one quotation mark. So we're going to go back to main, and I'm going to click on tune, but before I do, I know I'm going to get an error, and I'm doing it on purpose, so in case you see this error, you'll know what to do. So when I click on the tune button, it's going to shoot an error saying that the PID block contains unapplied changes. As I clicked around in these forms, you'll see that they changed to a pinkish hue, and if you hover over them, it'll say unapplied change. Even if you didn't physically change something, you left it the way it was. Once you click and click out, it assumes that you made a change. So all you got to do is hit apply. All those pink boxes go away. And then if I hit tune again, it'll work. Now what's happening is Simulink is looking at this complete loop, and it's looking at the parameters that we specified for our plant, and it is creating a linear model of our plant based on the parameter inputs. You don't need to know what that means, but just know that it works. And if you get any error at all before you get to this stage and see this window, post something in the comments and I'll try to help you out. But it should work. It should work without a hitch. And what you'll see is this window, PID tuner, open up. So what we're going to do is, I'll tell you what you're looking at, but first let's change the design mode from basic to extended. And we're going to click on this arrow to show parameters. Let's maximize. Plot is set to step and response is reference tracking. And you can uncheck show block response for now, and I'll show you how useful this tool can be later. So the way this works is, this tool assumes at time equals 0, we instantaneously change the set point from 0 to 1. So the output is trying to go to 1 unit, whatever that represents. In our case, it's 1 inch. And this blue line plots the output plots the system response of our plant model that we provided it. So in this case, this shows how the system will perform using a PID controller with these gains from going from 0 to 1. So in this case, if we instantaneously drove our plant from 0 to 1 using these PID gains, this is a crude representation of how our system would react. Now you gain a lot of good insight, and all the parameters that we care about for a controller are shown here. We have rise time, settling time, percent overshoot, and stability, all shown in this performance and robustness window. And the controller that comes up initially when this window opens are gains that Simulink suggest. So in this case, Simulink suggested a controller with these P, I, and D values. And the response, as you can see, the rise time is about 1200 seconds. And it takes about 4000 seconds to settle. So this is a pretty slow controller. It's very stable, very slow. And what you can do is you can also right click on here. You can change some of the properties. You can remove the grid. You can keep the grid. So if you remove the grid, you'll see that our target is 1. The blue line represents how the system will respond using these controller parameters. If you right click again, you can go to characteristics and you can check any one of these things. And when you do that, a little data point will show up on the plot and label what those are. So the steady state value, we'll see it's labeled here, and the steady state is 1. So this controller does eventually get to a point where there is 0 steady state error. We can show the rise time, and if we click on this point here, we'll see where the rise time is. We can also show settling time, and you'll click on here. That's how long it will kind of take to settle. So there's a lot of useful things that you can see here. So this is a very helpful and useful tool. And then we can also see peak response, and that's the maximum value that we hit. And you can see that we peak at 1.09, and that's about a 9% overshoot. So let's go ahead and uncheck all of these because we don't want to see them. I'll leave the grid off because it's more easy on the eyes to just see our target and our controller performance. So now let's look down here in this interactive tuning window. These are the tools that we will be using to tune our PID controller. So you have two sliders here. One is bandwidth and one is phase margin. As you increase bandwidth, you increase the aggressiveness of your controller. So as bandwidth increases, your controller wants to react faster. And what that equates to is having a faster rise time. If you decrease the bandwidth, your controller will be less aggressive, and that equates to having a larger rise time, but it may remove some overshoot and those things. Phase margin is another parameter, and as you increase phase margin, you increase the robustness of your controller. And what that means is you increase its ability to handle variations in its input. You want a very robust controller. You want to make sure that you increase phase margin, but however, when doing so, then you might modify the gains or undo something in a negative way. So it's a catch-22 when you move these two, and then sliding them back and forth, you'll see that these PID gains change accordingly to get to a response. You see these two arrows at both ends of the bandwidth. When you click on them, it changes the values of this bar by 10 times. So I can increase it 10 times, or I can decrease it 10 times, and that will allow me to, increase or decrease the bandwidth as such. And as I increase the bandwidth, see that my time changes accordingly. And now with a bandwidth of 3.71 radians, I get this rise time. And what you want to do for your PID gains is, we haven't talked about N yet. N is a value that is used to filter out the derivative term, because the derivative is susceptible to high frequency noise. You want to keep N between 2 and 25. Anything outside of that range, and that means your derivative is probably out of whack, and it's going to negatively affect your controller. So that's a design goal that you want to keep aware of, is always making sure what your N is. So what I'm going to do is I'm going to play around with these values and see if I can get a controller that I think is good. And what I'm looking at when I move these around is, first I'm going to set what I think my response time is going to be. Now, you don't want to set a response time that's too quick, because if you set something too quick, it may be faster than your mechanical system can respond to. So just keep that in mind, that you have physical parameter limitations as well. And you can see as I increase the aggressiveness, my N starts walking out of my desired range. So I'm going to step back a little bit. Oh, and one thing before I forget, these text boxes here are something that you can type in. Let's say you found a controller that you liked. You don't have to memorize the PID gain. Simply write down the bandwidth value and the phase margin value, and you can come back and type those in, and you'll see the same response to get the PID values again. I'll show you how we're going to use that in a little bit. So what I'm going to do is, I'm looking at the rise time right now, and that's pretty good. Setup time is 4 seconds. It's a little high. Let's see if we can get that down a little bit, but I think I'm okay with 4 seconds for now. That's even better. Setup time, approximately 2 seconds. The overshoot is pretty good. My N is within my desired ballpark range. I look at this plot, and it looks pretty good. There's not a lot of overshoot. There's a little bit, but that's okay. So what I'm going to do is, I think I'm okay with this controller based on this plot. I want to put it on the C-Rio and see how it performs. So I'm going to hit the apply button, and right now I cannot copy these values. So what I do is I hit the apply button, hit OK, and those values that were there are now copied to these text boxes here. So I can Control C, switch over into LabVIEW, and I'm going to well, let me stop this project. You don't need to stop it, but just to keep my sanity, I always like to stop it. And I'm going to paste the p-value in there. Do the same thing for I and D as well. Okay. Control C. And one of the other things I like to do is, this is just for my sanity, once I change these values, I like to go to data operations and make the current and check make current value default. The reason I do it is because you see, I can change values all day. LabVIEW doesn't really recognize a change. There's no asterisk here, making sure that a change did occur. Once I make this current value default, you'll see a change was instantiated, and it's going to ask me to save. And I'm fairly confident that when I deploy this code, it's going to use these values. What I'm also going to change is the max negative output. I'm going to make max positive output 1 and max negative output -1. The minimum negative 0 and the minimum positive 0 for now. And so what this says, what these 4 boxes say is I can have any value between -1 and 1 coming out of my PID controller. And that's akin to what we would be supplying a motor controller if we were a joystick input. So I like the way this is all set up. What I'm going to do is I'm going to go to robot main and run, and it's going to ask me to save. It's going to do its thing. Okay, now before I enable, I'm just going to make sure I'm in manual mode. And I'm going to go over to the driver station, hit enable. And so what I'm going to do is I'm going to, let's just make my set point 400 or around that area. And once I switch into PID mode, it's going to kick in. Before I do anything, I want you to see something on the PID front panel. Right now the PID loop is running. Just the output is not being sent to the motor because this switch. You can disable the PID loop from running when you don't need it, just to save processor power by simply putting it in a, enable if block or something. I didn't do that right now. But I want to explain what this graph is showing because it's very useful. So the white line represents our maximum output in the positive region, and the red line represents our maximum negative output, 1 and -1. The blue line represents what the controller wants to do, or what the output would be if we didn't place any saturations on it. So the blue line represents, if this controller had no limit, the blue line is what it would be outputting to the motor controller. The green represents what we allow to pass to the controller. So the green represents the values that are acceptable. And the reason why you're seeing all of this high frequency noise is from the derivative term. Now the derivative is very susceptible to high gain noise, and we can see that here. I'll show you how we get rid of that. Even though I call it simple PID, I implement some very advanced features that are going to help you when you tune. But I'm going to leave it for now just to show you what derivative noise does to a controller. So I'm going to run this. We set it to 400. I'm going to go to enable, and I'm going to switch to PID. That wasn't too bad. There was some hiccups in the beginning, and you can see this is what our controller did, and it came down and it stopped. But we ran to 400, and we got there, and there was a little bit of undershoot, so it slowed down, and then it went there, and it looked just like our, looked similar to what Simulink thought the controller would perform. But you saw the hiccup that happened in the beginning? That was because we have this high frequency noise. Let's try to do it in the reverse. Like you can see, we have a nice undershoot. It's going there. It's taking some time to get there. And we look at our current value. Right now, our acceptable error difference is 0. So what that means is we're telling the PID controller that the current value and the desired value have to have an error of 0. So there's no tolerable steady state error. Depending on what your application is, you may be able to tolerate an error. For example, if I were doing position control on the drivetrain and I just wanted to drive forward 300 inches, depending on what I'm doing, I may be able to tolerate if the robot landed, 1 or 2 inches away from its mark. So if that's acceptable, I can increase this however many units I'll tolerate, plus or minus. And right now I set it to 2 inches. So if I increase this, you'll see it stopped, and the current value is 425 inches, and the desired value is 426. So it's about an inch off in this case, and it's going to be random depending on how it is. You'll see here we're about 2 inches off. So play around with this, and if it is 0, and the reason why I always stress there should be some acceptable error. If it is 0, what that tells the controller to do is make sure the current value matches the desired value. So what's going to happen is the PID controller, any PID controller, is going to constantly iterate and try and make these values 0. And that's going to mean oscillations around your set point depending on how well your gains have been tuned. Right now we don't have that problem. Because our gains are pretty good. So right off the bat, you can see how close we got just by trying one more time. I do notice that there's a lot of undershoot, and it takes a long time to get to where I want. I'm going to try and increase that, and I'll show you how to do that. So that means that we need to make our controller a little bit more aggressive than what it is currently right now. So what we're going to do is we're going to go back to Simulink, click on the tune button, and try and make a little bit more aggressive controller. So we'll switch to extended mode again. I'll click on show parameters and maximize. So this is where the show block response becomes very useful. The blue line is always what we're currently monitoring. The block response represents the last PID values that we had. And as you can see, Simulink again tells us that it thinks these are the best values for us to use. And we obviously don't agree. So what we're going to do is make this a lot more aggressive. So we're going to click on this until our time gets into the right band. And now as we move this value, you can see we're controlling the blue line, and we can compare how our new values stack up against our old controller. And just looking at this right now, the new values that we have has a very large overshoot when compared to our previous controller. It also takes longer to settle, and that's without looking at any of these parameters. Now if I look at these parameters, I can confirm what I see visually. The rise time is larger in the new controller versus what we just put on the C-Rio. The settling time is way larger, close to 10 seconds, and the overshoot is almost 10% larger. So our problem was we wanted to make the controller a little bit more aggressive. So let's find a controller that's more aggressive than our previous one. What I'm going to do is I'm going to make it more robust. That's going to bring the overshoot down. And maybe I'll leave it right there. And so that's very close to our old controller. Now I want to make it a little bit more aggressive. And if, like I said before, if you noted what our old controller was, if you noted the values of our old controller, you could just simply type them in here again, and you'd get the same exact controller, and then you could start from there. We're close enough. We're close enough right here. Now we want to make it more aggressive. So as I make it more aggressive, I'm looking at my N value, and I'm seeing my N is getting out of my desired range. So I'm going to just keep playing with this and hopefully find a combination that's suitable. Okay, so I look at this and look at my rise time. My rise time is 0.187. It's a little bit quicker than before. Settling time is a little bit quicker than before. The overshoot gets hurt a little bit, not too much. I think this is probably tolerable, but my N is in the region I want it to be. So I'm gonna go ahead and try these gains out. Well, maybe so I'm gonna go ahead and try these gains out. I'll hit apply, and what I'll do in this case is I'll note these values: 7.4 radians at 68 degrees. And I'll write that down, and that will give me this controller again if I ever wanted to revert back to it. So I hit apply, and what's going to happen is after I hit apply, I'll hit OK. Those new PID values are copied in here, and I'll go ahead and copy these into LabVIEW. Now what I'm going to do is I'm going to leave the project running, switch this over to manual mode, and I'm going to run it in real time just to show that you don't have to shut it off. And it should work all the time. I've had some issues though with it, so just for sanity, I suggest disabling, copying these values, and then re-enabling. But I'm gonna show you both ways anyway. Okay, so now we have our new PID gains in here. I'm gonna switch over to PID mode. Right now, because we were still running, our target value and our current value match. I'm going to just send it to 100 inches. And you can see automatically that was a lot quicker than where we left off before. So we have a response time that's a lot quicker. There's still a hiccup there. If you noticed, when we run, there's still some jerkiness. That jerkiness is caused by the derivative, and the PID controller that we have can definitely fix that, and I'll show you how in just a little bit. What I want to do first though is I want to make it a little bit more aggressive so that I'm not undershooting as much as I am. However, just to note, right now our acceptable steady state error is 0. If I increase this to 2, I may get rid of my undershoot or my overshoot because I'm allowing for there to be an error. So let's try that and see what just happens. Okay, so what I'm gonna do is let's make this a little bit more aggressive. And just to show you something, I'm gonna switch into manual mode. Create some differential. Now the PID loop is running. You can see it's telling the motor to drive, but the value on the output is having huge swings. That huge swing is caused purely by the derivative term. If you had a PI controller, you would not have this, and I'll prove that by changing the D value to 0. And once I do that, you'll see there's no more high frequency noise. The output is completely steady. Now, if I run this, the controller is not going to behave as it used to, but the jerkiness went away. This controller, the controller that I developed, implements a derivative filter that I don't have enabled right now. I can simply turn it on with this button right here, and that's an input to the terminal. So what I'm going to do is I'm going to put the derivative value back in, and I'll show you how this derivative filter works. So I forgot what the value was. Let's go ahead and copy this guy. Let's put it back in. We'll start to see our noise again. There's our noise. Now I'm going to enable the derivative filter, and this is in the simple PID. This is also an input to the PID block. So once this is enabled, the R term specifies how much filtering to do. The lower the value, the more filtering. So as I lower this value, and what I'm looking at is the output variable up here. I'm seeing when it goes steady, and you can see maybe around here it's still fluctuating. It starts to go steady around 0.5-ish. Down in the 0.1s, it's completely steady, and you'll see that noise just completely went away. And if I run this controller now, there'll be no more jerkiness. There you go. That's beautiful. So as you can see, we probably spent 15 minutes on this, and I have a controller that now I'm just trying to make it perfect. But the gains that I got right off the bat from Simulink were a great starting point, and this is something that I would put on my robot today for what I'm using it for. I usually keep an acceptable steady state error of 1 or 2 in this case. So looking at this with the derivative filter there, the acceptable error there, you can see the response is very quick, and I still have a little bit of undershoot, so I'm going to make my controller just a little bit more aggressive and get there. Now, if I were overshooting, I would try and make it less aggressive. One of the other things that you got to make sure is when you're doing this that your controller is in brake. And I'll show you, I'm going to switch my motor controller to coast mode, and I'll just show you how completely different the response is. Okay, so my controller is now in coast mode, and what I'm going to do is, it was in brake before, so now I'm just going to drive it forward. Now you saw that oscillation. That oscillation is because the motor was allowed to coast. So when the PID switched from a positive to a negative, the motor was still allowed to freewheel in the opposite direction, causing the PID over here to oscillate, and it's oscillated around its target point. We'll do that again. And you can see that oscillation is simply caused by just how you set your motor controller. So depending on what you're doing, you'll want to make sure that you're in the proper mode. For position control and for speed control, I always recommend putting it in brake mode. So I'm going to switch it back to brake mode. So my controller is now back in brake mode, and see, there's our response. So what I'm going to do is I just want to make it a little bit more aggressive, and that's just my personal taste. I'm showing you how to look at these values, go back into Simulink, and tune your controller for your desired application. Make sure you go into extended mode. Your plot is step and reference tracking and showing the parameters. And again, Simulink is showing you what it thinks your response should be. You know what I'm going to do? Let's try what Simulink response is. I've already noted down what the previous controller was where we left off. It was 7.4 radians per second at 68 degrees. So when I look at these values, I know that there's going to be a problem with it, and I want to implement them right now, just so if you run into this problem, you'll know what to do. So I'm going to hit apply, hit OK, and I'm going to copy these values over. Hopefully this will work in real time. I usually have trouble copying values over that are in scientific notation that are given out by this function block. Sometimes when you put it in LabVIEW, what happens is it truncates the value, and I'm not sure if it takes everything after the E. I've had situations where it truncated the value after the E, and it basically converted it from e to the minus 13 to an integer of 1.97. So just be careful about that. Obviously right now I'm not having that issue. Okay, the D was the last one, and there you go. So this is running in real time, and what I'm going to do is just drive this negative, and nothing happened. The reason why nothing happened, and this is because the gains are too small. The gains are so small that they're approximately 0. E to the minus 8, e to the minus 13, e to the minus 5. They're so close to 0 that when the calculation is being done, it's not within the deadman. So the value that the controller is outputting is so low that it's not even driving the motor. It's too close to 0. So no matter what you do on this set point, there is an error. You can see the error is there. The PID controller loop is working. Just the values are so small that your physical system is not being controlled. So if you ran into a situation like this, that's why it's very helpful to see these output variables that I have here. You can see the output variable is 0. Here's another thing that I just noticed that you might get caught up on. Right now it's saying 7.8 or something. This is in scientific notation. It's being truncated off because this window is not large enough. If you expand this window, you'll see an e to the minus, I guess, 7 after it. So extend this window when you're looking at this number to see what the real value is. Right now, it's still way below 0. So if you run into this problem where you're moving your controller and nothing is happening, look at the output variable and verify that you're actually getting something. Look at all the components that make up the algorithms, basically this value plus this value plus this value, and you can see this is e to the minus 6, e to the minus 8, and this is probably similar. So therefore, your output is going to be so close to 0 that it's within your deadband and you're not driving your motor. So I'm going to go back to Simulink and click on Tune. And go to Extended, Show Parameters, and Expand. Now remember, the gray line represents the previous controller that was applied, but in this case the previous controller was a Simulink suggested one which didn't work for us. I want to replace it with our last known good controller. This way I can compare the new controller that I'm tuning against my last known good configuration. I can do that by applying my last known values and restarting the tuning block. And what I'm going to do is, I already know where my last controller was. It was 7.4 radians. I got to hit enter at 68 degrees and hit enter. And I'm going to uncheck that. And that was my previous controller. That's where I left off. So what I'll do is I can hit apply, hit OK, click on tune again, and set this back up by changing it to extended, showing parameters, and expanding. And now if I type it in again, 7.4 at 68 degrees, my two controllers match, and now I'm at my starting point, and I can modify this controller with respect to my previous one. Alright, so I want it to be a little bit more aggressive. So let's see. And just by changing this a little bit from 67 to 68, you can see the huge swing in parameters. At a phase margin of 68, these are my gains. N is at 26, rise time is 0.142 seconds, settling time is 1 second, and overshoot is 4%. If I move it down 1 degree, you'll see overshoot just increased 1.5%, settling time increased 1 second. So just one simple change of this will allow you to create completely different performance characteristics. One last thing I didn't show you was these ticks here, these ticks allow you to do fine control of the values. So instead of, let's say the slider, if you try to drag the slider, it's really hard to do like a 0.1 or a 0.2. This is a decimal point control. So clicking on this tick will allow you to do more finite control if you think you're in the area that you want to be in, but you just, you want to move it up or down a little bit. So I'm going to make this 68. I'm going to increase this guy until my n gets to, right now my n is at a point where I'm okay with it. So I think I'm happy with I want my n to get too large. I think I'm happy with where this is right now. 9.8 at 68 degrees. And that just makes it a little bit more aggressive. And we'll see what happens. So I'm going to hit apply, copy this over into lab view, paste it in real time. Maybe I should disable or go into manual mode. You can see it just jumped because I was still in PID mode and I just gave it some proportional control. That showed you that the controller was working. Paste this guy. And lastly, the derivative. Okay. Okay, so these values are copied over into LabVIEW. And what I'm going to do is I'll just run it. That was pretty good. There you have it. There's a control, and I can, make it more aggressive if I want to. One of the other things that I want to talk about is the min-negative output. This controller works very well for large swings, but what about short distances? Let's say right now we're at 492. Let's say we just wanted to go to 490. So if we typed in 490, well, let's make this 0. Let's see how it operates at 480. Now you see what happened is there was just a large swing, and then a very long time it took in order to compensate. And it's still trying to compensate now. It's compensating only because I have a 0 error, and there it is, but let me just make it 1. Let's just do 470, 450. So that wasn't too bad. I just want to gain more room up at the top spectrum. So if I did, a couple of inches, 260. It also performs very well at the low spectrum too. So that's just one thing to make sure when you're looking at your controller. Your gains for large swings also accommodate for small error changes as well. For certain instances is when you move a small error amount, like right now if I moved, let's say, to 53, this worked very well for me, but in certain cases you might see it takes a very long time to move, And the reason is because if you look at the output of the gains, the reason it's taking a long time to move is because the output that is being provided by the gains is probably smaller than your deadband. When I switch over to manual control, and when I was trying to move the motor manually, you can see I have a really large deadband, roughly about 0.2 in the forward direction and about 0.3 in the reverse direction. So if this controller at any given time was issuing an output value in between negative 0.3 and 0.2, the wheel wouldn't move. And so what eventually will happen is the integrator will continue to increase because the error is still there, and eventually it will move. However, it will take a very long time, and that problem is known as is deadband error, because your controller is working and telling your motor to move, but the deadband of your motor is not causing it to do so. In order to overcome that, you can replace the minimum negative output and the minimum positive output values to be the minimum values that your controller will output. What this will allow you to do is get rid of the deadband. So if I set this to 0.23 and set this to negative 0.322, whenever there is an error that requires the controller to initiate an output, what will happen is it will not output anything in between your deadbands. So it will always at least provide enough power to move the motor a small amount. You want to make sure this is right above your deadband, and if it's still too slow, you can increase this slightly such that your response is a lot quicker at the lower end. So if I run this the way it is, I think my motor is going to just jump real quick. All right, there it goes. Let's see how the response is. For large distances, it's still roughly the same. And for short throws, like, let's do, you can see our errors. Our errors, it always stops within our acceptable error. And I always like to keep something on there just so that it's not always trying to get true zero. Let's go to 165. You see that was, well, you probably didn't notice, but that was probably a lot quicker than what was happening before. And if you ever have trouble where when you do a short throw, it's not going, that's because your gains are such that it's so low that the PID controller is outputting something within your deadband. However, this is great. This controller, I'm pretty happy with. And so I would probably push this to do further testing with on an actual robot, run it in its environment, and see how well it holds up. So one of the last things I want to talk to you about is this enable gain schedule button down here. One of the other advanced features of the PID algorithm that I implemented is to accommodate cases where you have what's known as an unbalanced load. And you get into these scenarios when, let's say, you're driving an elevator lift up and down. So in the up case, you're driving against gravity, and so you need more you need a more aggressive controller to push against gravity. In the down case, you're driving with gravity, so you need a less aggressive controller because the more aggressive one will just cause it to descend more rapidly than your comfort zone. So when you have an unbalanced load like that, a way to solve it is known as gain scheduling, where you use multiple sets of gains for different scenarios. The algorithm that I put together has the ability to accommodate two scenarios. One set of gains for when your set point is greater than your current position, and another set of gains for when your set point is lower than your current position or less than your current position. So for example, if I were moving an elevator and my set point was greater than my current position, that means it was going up, I would use one set of gains that had a higher aggressiveness. And then for the reverse case, going with gravity, I would have another set of gains that was less aggressive. Now, you need to take gravity into account when you calculate your load on the motor for each case. And when you have an unbalanced load, you've got to split it up into two. Calculate the gains for the forward and then calculate the gains for the reverse in two separate scenarios. So when you click on the Enable Gain Schedule button, what happens is when you look at the simple PID inputs, you have two sets of input. PID1, which were just blind copies of these sets of gains, and then PID2. If you look at the VI for it, I'm just going to switch into the back end really quick. If you look at, it's two back end. If you look at the back end for the VI, it contains 3 extra ports on the bottom that take in a second set of PI and D values. That's for the second gain scheduling controller. So when this is enabled, it will initiate these values in the reverse case. So when I move this motor forward, it's going to use these current values. However, once the error drops to be negative, or where my set point is less than my current position, it's going to use these values. We'll just try that out right now. Now, as you can see, when you look at PUs, IUs, and DUs, this is where it comes really handy. Now, in the forward direction, it told me that the gains that it used were the first ones as I'd expect. In the reverse direction, you can see nothing is happening, and PUs, IUs, and DUs switch to 0. Now, because I had these gains set to 0, that means my output is 0, because anything times 0 is 0, so nothing is happening. If I increase this to 1, something is going to happen, but I'm not going to like it because it's not tuned properly. So, but let's just do it. And I can't do it here. I'd have to, because it's clamped to 0, I'd have to do it in teleop by providing an input, which I'm not going to do. So play around with it. Although when dealing with situations like this, I highly recommend to try avoid an unbalanced load as much as possible. For example, if you're doing an elevator lift, try and counterweight it. If you're driving up inclines or driving down declines, that's probably where you can't really get away from having gain scheduling. So that's just another advanced feature that's rolled right into this simple PID for your using gain scheduling. So there you go. That's tuning a PID controller the easy and simple way. Hope this was a very useful resource for you, and please provide any comments or questions or feedback that you may have on the method that I showed today. I'd love to hear what your experience is. Alright, so let's talk about some pitfalls and gotchas. I guess one of the first questions that you're probably thinking of is, can you use this method to tune gains for any PID controller? The answer is a resounding yes. As long as your parameters are properly calculated, the gains that will be provided to you by the Simulink function will be very close to the ideal gains for your system, as long as you make sure you stay within the filter coefficients. Now, however, I ran the gains for a custom PID controller that I personally implemented. The controller I use has advanced features such as derivative filtering, integral windup prevention, as well as deadband removal. All of these advanced features make this controller respond better than a standard PID controller. I've made this controller available to the FRC community, and I encourage you to use it in your next robot. If you do, I'd be happy to hear about your successes or any failures that you ran into. So please go ahead and email me and let me know that you're using it and tell me what your experience is. However, if you're using another PID controller, be aware that no two PID controllers are the same because of the various ways that you can implement the PID algorithm. You have a parallel form, an ideal form, a series form, and then you have all these other advanced features. So you may run into issues where the response you get from Matlab Simulink when you put those PI and D gains into your other controller, you may observe an awful response. Some common problems that you may run into is if you have a jerky response like you're seeing in the beginning of this video, it's because your derivative is too high and you need to either implement a derivative filter or lower your derivative. Make sure that that filter coefficient of n is within the acceptable range. Keep it between 2 and 30. It's not an exact science, but the higher that n is, it means that your derivative value is way higher than it needs to be. If your response overshoots and stops, but then it takes a really long time to get back to your set point, what you probably have is integrator windup, and so it's just taking a very long time in order to command your motor to go in the opposite direction. Lower the integral term, or implement some sort of integral windup prevention method. The algorithm that I have, I use a clamping method. There are other ways to overcome integral windup. If you notice oscillations in your response around any point, especially around your desired set point, your P is probably too high. So lower your proportional term and then see if that works out for you. If you're using another controller, be aware if it's ideal or parallel, because in the ideal case, changing your proportional term will affect the integral and derivative term as well. The controller that I provide is implemented using the parallel form. So changing any of the gains, P, I, or D, won't affect the others. So that's why it's very important to know the implementation that you're trying to tune, because if you don't, you're going to run into a wall and get frustrated with trying to tune a PID controller that's not implemented the way you think it is. Make sure the final gains that you run are tuned when you're running the robot in its natural environment. It's okay to try and tune the gains for the first time with a robot on bricks in order to get a ballpark response. You got to run it under load, because what might work when it's suspended will probably be too small and underperform when it's under load. You got a 120-pound robot that's on those wheels. It's definitely going to be a noticeable difference. So if you run into a situation where you tuned your gains and everything worked well when you did a bench test, but then when you put it on the robot and ran it for the first time, it looked really slow and it wasn't efficient, that's because maybe your controller is too conservative, and try making it a little bit more aggressive, and that should probably help it. Always be aware of brake versus coast mode on your motors. As you saw, having either coast mode or brake mode affects your response. When you're in coast, you'll have larger overshoots than you will in brake mode. Always be aware of your battery voltage when you're tuning. That's probably the most common problem when tuning a controller, because you probably spend 15 or 20 minutes and then you're tweaking gains and trying to get the perfect controller, all while your system is running. After about an hour or so, your battery is getting drained because you're pushing your motors hard, and you start to see your controller underperform, and you've changed your gain so many times that you're starting to get frustrated. The only real reason why your system is underperforming is because your battery is too low and that's not providing enough current to your motor. So always make sure you got a topped off battery when you're going to sit down and tune your controller. Keep in mind, mechanical design is very important when dealing with a control system. A controller cannot really accommodate for poor engineering design. Try to avoid unbalanced loads. Try to make sure that your mechanical system is built with the idea of being controlled in mind. Try to remember to set your steady state error to a number greater than 0. At a minimum, the value should account for the minimum error between your encoder ticks. Make sure you choose an encoder with a count that will provide you higher precision than you need. Also, make sure you're sampling the encoder value fast enough to feed the PID loop. If you don't sample it fast enough, you'll get a jerky response, because your set point position will be trying to compare to a very slow current position, and you'll notice a jerky response. Depending on what you got running on your robot, 10 Hertz is probably overkill, so you can probably slow that up a little bit and still get a very great response from your PID controller. Another useful fact is you probably only need to use PID controller some of the time, not all the time. So put it in a block where you can turn it off when you're not being in use, and that will save you a lot of processing power for other things. The Simulink model I provide you to use to tune your gains is a generic model for any drivetrain configuration, so it should work for anything you need it for that involves a motor driving a load. Just make sure that you supply the proper motor parameters and calculate the motor load's inertia correctly, and it should work great for you. If you have any troubles at all, please just post a question. So that's all I had. If you had any questions, any comments, or If you appreciate what we're doing, please go ahead and post comments. We always appreciate feedback from the FRC community. The 2012 kickoff is in a couple of hours. I wish you all great luck. The reason why the aluminum Falcons are doing this is in order to give you guys a head start, help you gain better control over your robots without having to go through the frustration. Please use the tools, and if you have any problems at all, we're here to help. So thank you for watching, and on behalf of the Aluminum Falcons FRC Team 2168, we wish you great success in the 2012 season.